Well, hello once again, everyone, and welcome officially to our webinar. Today's topic is on DEM extraction with synthetic aperture radar data. The webinar today is going to be looking at extracting elevation models from radar data, and just quickly a description on what it is that we'll be covering. We will be looking at using commercially available radar imagery from RadarSat-2. And the focus of our webinar is actually on a case study that we've prepared using a stereo radar image pair over Santorini, Greece. So the topics we're going to be covering include data collection considerations. We've collected the data in a certain configuration for the webinar. And we'll be looking also at our new DEM extraction tools that are available within Geomatica. And we'll also look at filtering and editing the DEM to fix interpolation errors and just generally improve the quality of the DEM. And we'll also be looking at how to do some quality assessment, and we'll also be showing you some other DEMs that can be derived from other sources of imagery. Just really quickly, the topic of today's webinar is on extracting elevation models from SAR Imagery. Now, I just want to preface the whole webinar by saying that although radar imagery is very useful for collecting data where you have issues with pervasive cloud cover and illumination issues with just with the ability to get a good strong imagery. The quality and the resolution that you can attain with radar imagery is, of course, very different from the quality that you can attain with other types of data, such as high-resolution satellite imagery and high-resolution air photo imagery. So the level of detail, just the level of information that can be obtained from the DEMs is very, very much dependent on the input data. So we hope you're here today because you're perhaps having issues with optical imagery, collecting radar DEMs over certain areas, but we just want to make sure that you know that Geomatica can process lots of other data as well. So if we quickly go to the next slide, we just want to remind you of a few logistics during the webinar. So all of the lines will be muted, and also you can use the questions panel to communicate with us at any time. So you could just pull up the questions panel and let us know if you have a specific question. You can also raise your hand. There's a little raise your hand option in there. We can use that during the question and answer period. Hopefully you're set up with a computer where you've got audio. Perhaps you've got a USB headset plugged in, or you're dialed into one of the conference lines. And also, we are recording this webinar, and you can definitely come back and review certain parts of it later on, but we'd love it if you were to stay for the whole session and interact with us in person. That would be fantastic. Next slide. So just a few words on who's on the line today. So myself, Kevin Jones, I'm the Director of Marketing, and I've been with PCI for about 6 years now, and I've actually been working in the industry for 18 years in the remote sensing Earth observation industry. And it's a pleasure to be here today. And on the left is Jean Bouffard. Jean is located also in our Ottawa office, and he's been with the company for about 3 years now. And Jean is a remote sensing specialist. He has both an undergraduate and a graduate degree in remote sensing. And Jean is an expert in our technology. He knows how to work with all of the various technology that we offer, and he works directly with our customers around the world to ensure that they are successful with the various technology that we offer. Next slide. So just a few quick words on PCI as a company and the products that we offer. So this nicely summarizes what it is that PCI can offer and how it is that we solve some of our customers' challenges around the world. So we have a platform. And what do we mean by a platform? Essentially, we have multiple tools that are available that can be used to solve problems of varying degrees of complexity. On the left, we have Geomatica, which is our desktop image analysis product. And Geomatica has over 550 algorithms that can be executed typically independently or a few of them put together into a workflow. And on the right, we have GXL, which is essentially our high volume production system. And so the technology is the same, but the implementation is slightly different. In the case of the GXL, we're working with terabytes of data on a daily basis, and we can deploy a parallel system to handle very, very high volumes of data. In the middle, we have a Python icon there, and that's because we can use open source programming language. We can use Python, which is an open source programming language, to automate different tasks. And so this is very important if you're trying to repeat certain operations and gain efficiencies in how those operations are done. So that represents our platform, and depending on what type of implementation is put into place, we obviously can achieve different operational efficiencies, and all of our technology is extremely scalable and flexible. Go to the next slide. So what are we looking at today? We're looking at our improved DEM extraction capability. This is something that PCI has invested heavily in terms of improving, and we have some of our top scientists working on this problem and have been working on this problem for several years, and most recently they've put quite a lot of attention on this problem within the latest releases of our software. Now we're about to release another version of our software very soon, within the next few months, and this particular capability just keeps getting better and better. So what we'll be working with today is our current version of our software, which is Geomatica 2015, and what you'll see is that we have essentially the ability, through the techniques that are used in the software, to achieve a higher level of quality from the same input data. The processing has been optimized to be faster, and we have a lot of really great tools for editing the DEMs, and that's something that we've added in the last couple of years, and you'll get a sense of how really potentially useful these tools are for handling all sorts of problems with elevation models. Next slide. So here we see a digital surface model that has been derived at roughly 45 centimeter resolution over a location in Canada. And you could just see the stunning level of detail here. We can see micro elevation that's related to the terrain. We see small slopes on here. We can see vegetation. So these are tall trees. We can see individual vehicles that are parked along the various parking areas here, and we can also see this really interesting structure here. This is a military facility in Quebec City, Canada. And even down here, we can actually see the slope. There's a very steep bluff that goes down to the St. Lawrence Seaway here. So this gives you a sense of the level of quality that could be attained. My apologies, I mentioned 45 centimeters. It's actually 30 centimeters in this case. So that's an example of a DEM that could be extracted from aerial imagery. If we go to the next slide. Now the input imagery for that aerial-based DSM is of higher resolution. I believe the input resolution was 15 centimeters. In this case, we're working with spot 6 data. Now, the spot 6 panchromatic resolution is, I believe, in the 50 centimeter range, and the level of detail that could be attained is again a little bit different, but you can again see some very nice terrain features, natural terrain features, and also some surface features for this particular DEM, which is over Barcelona, Spain. And with that, I'm going to pass things over to Jean, who's going to walk us through the case study on Santorini. Jean, take it away.
Okay, well, thank you very much for that introduction, Kevin. So now that you've had a quick look at aerial and optical DMs that Kevin demonstrated, we're going to look at radar DMs now. More specifically, I'm going to demonstrate a DEM extraction case study over the island of Santorini. Now, the main purpose of the case study is to examine DEM extraction using SAR imagery within ortho-engine. For those who are not familiar with ortho-engine is an application within our Geomatica product for photogrammetric processing. Now, extracting DEMs from SAR imagery, as Kevin said, could be a difficult task. So in addition to extracting the DEM over the island of Santorini, we're also going to look at best practices for selecting SAR imagery for the purpose of DEM extraction. We're also going to look at editing DEMs extracted from SAR imagery to remove artifacts and to improve the overall quality. And we're also going to finish off by comparing our extracted DEM to other DEM products. So our study site for this case study, like I said, is the island of Santorini, Greece, located in the southern Aegean Sea, approximately 200 kilometers from mainland Greece. As you can see in the image, Santorini is part of an archipelago, and the grouping of islands right here is known as Cyclades. The island of Santorini is approximately 91 square kilometers in area, and beside the island of Santorini we have the island of Terasia, and this island is approximately 9.2 square kilometers in area. So the topography of both these islands is considered mountainous, and the terrain is quite rugged, as you can see in the image right here. The interior coastline of both islands, you have steep coastal cliffs that range between 0 to approximately 300 meters in elevation above mean sea level. The overall elevation for the entire area ranges about from 0 to approximately 575 meters. So considering the topography of both islands, and the fact that our radar scenes will cover a lot of water, this makes for a very interesting SAR DEM extraction case study. So to begin, let's quickly go over the concept of stereogrammetry, which is the approach we use at PCI for DEM extraction. Now, stereogrammetry is a method of reconstructing relief from a pair of stereo images. In other words, we're extracting elevation from overlapping stereo images. To briefly explain how stereogrammetry works, here we have two sensors acquiring information over an overlapping area. Using the overlapping portion, what we do is image correlation to identify and match corresponding pixels between those two images. Using the matched pixels from the image correlation, we then determine the displacement along the y-parallax. Then using that known displacement, in conjunction with the sensor geometry, we're able to derive the elevation values of those pixels. So for this process to be successful, there are a few things we need to take into account when selecting a pair of stereo SAR images. Now, to ensure we can extract the best possible DEM, here are a few things to consider. The first item is the acquisition mode. And with RadarSat-2, which is a SAR imagery I'm using, it's suggested to use either fine, multi-look fine, or ultra-fine. And these acquisition modes provide the best compromise between spatial coverage, resolution, and noise floor. For the polarization, it's preferred to use single polarized HH. Next, we have the angle of incidence. And this is very important, this one criteria right here. And ideally what we're looking for is a minimum angle of approximately 30 degrees, with a separation of about 10 to 15 degrees for the second image. So if the first image has an angle of incidence of 30 degrees, the second image should have an angle between 40 and 45 degrees. For the look direction, it suggested that both passes are sensing from the same side. Now the pass direction itself, it doesn't matter if it's descending or ascending, as long as it's the same direction for both images. Now, if you're intending on extracting a DM over rugged terrain, it's suggested to acquire two stereo pairs. So you have an ascending pair and a descending pair. And each pair should have opposite look directions. This is to minimize the amount of geometric distortions. The last item is a temporal interval, which is the time lapse between when both scenes were acquired. For this, it's suggested to keep the temporal interval as minimal as possible. Now, another reason why you may want to consider these items for scene selection, in addition to simply the requirements for stereogrammetry, you want to reduce the likelihood of the extracted DEM having artifacts, such as layover and foreshortening. To quickly go over these two sources of distortion, layover is when an elevated feature appears to be leaning. In the image right here, you can see that the peak of the mountain is leaning over the base of the mountain. And on the other side of the mountain, it appears to be stretched. So this problem occurs when the radar signal reaches the top of an elevated feature before it reaches the base. And that signal is received before the signal from the base is received. As a result, this causes a shift, and you get these layover effects as seen in the image. And layover issues are quite common with mountainous areas such as Santorini. With foreshortening, the radar signal attains the base of an elevated feature that is tilted towards the sensor. Before the signal attains the peak of the elevated feature and is returned to the sensor, as a result, the slope appears to be compressed. So if you look right here, you can tell that the slope in the Santorini radar image is much shorter than the actual slope looking at the Landsat 8 image. Also, you can easily identify foreshortening in your images. That's very obvious by these bright features right here. So now that I've provided the best practices for scene selection, here's a summary of the SAR imagery I have for this case study. So for the acquisition date, I have a small temporal offset of approximately 3 days between June 3rd and June 6th. For the acquisition modes, I'll be using 2 scenes with ultra-fine wide. For the incidence angle, my first scene has an angle of 30.4 to 33.8 degrees, and the second 45.7 to 47.5 degrees. This is good as it conforms to the suggested incidence angle guidelines. However, Santorini is quite rugged in terrain. It would have been better to have the second image at approximately 40 to 45 degrees, but this is still good. The polarization for both my scenes, they're both HH. The orbit direction for the pair is ascending. However, once again, we're covering very rugged terrain. It would have been preferred to have a second stereo pair that's descending. And both scenes were acquired looking at the same direction. So there are a few shortcomings when it comes to the scene selection here, but overall we have a good stereo pair for DEM extraction. So now I'm going to present to you the workflow to extract the DEM of Santorini in OrthoEngine. And afterwards, I'm going to edit and improve the DEM in focus using the DEM Editing tool. So basically, there are 4 main steps in OrthoEngine and 1 step in focus. In OrthoEngine, we'll be looking at project creation and importing the data. Then we're going to look at point collection and the bundle adjustment procedure. Then epipolar pair selection and generation, and finishing with DEM extraction and geocoding. And then in focus, we'll do DEM editing. So let's begin. So the first thing we're going to want to do is create a new OrthoEngine project file. So what I'm going to do, I'm going to go to File, I'm going to go to New, and this panel right here is going to pop up. And I'm going to want to specify a radar project type. Now in OrthoEngine, you're able to select multiple different types of projects: aerial, optical, radar, polynomial, etc. I'm going to want to select radar. And once I select on the radar project type, you see right here that there's 3 different models I can choose from. For this case study, I'm going to use the 2T model to compute the position and orientation of my scenes. Afterwards, I'm going to specify an output file name, and I'm going to click on OK. Immediately after pressing OK, the Set Projection panel pops up. And what I need to specify here are three things: the output projection of my orthos, the output spatial resolution of my orthos, and the projection for my ground control points. So the first thing I'm going to specify is the output projection. And I'm going to specify to its, I'm going to set it to its appropriate UTM zone. So I'm going to click on the drop-down, go to UTM. I'm going to set the datum to WGS 1984. I'm going to set the zone to 35. And the row to S, which is the 32nd latitude parallel to the 40th. And now I'm going to set the spatial resolution of my images. So I'm going to set it to 2.5 and 2.1. Now for the GCP projection, I'm simply going to assign the output projection to my GCPs. To do that, I'm simply going to click on Set GCP Projection based on Output Projection. I'm going to click OK. Now the next thing I'm going to want to do is add my imagery to OrthoEngine. So if we look at the processing step drop-down menu right here, you can see that all the photogrammetric processes are correctly sequenced, which makes it easier for people to work and produce orthos in OrthoEngine. So I'm going to go to Data Input, and I'm going to click on the second icon right here, Read PCI Disk File. The Open Image panel is going to open, and I'm going to click on Add. So right here, I have my two radar scenes that I'm going to use for this project. Now, some of you may notice that I've already converted or imported my radar SAT imagery into the PCI disk file format. And I applied a sigma naught calibration type to my images. Now for DEM extraction, when it comes to the calibration type, it doesn't matter what calibration type you use, as long as you're consistent between all your images. So now I've added my two images to OrthoEngine. Okay, now the next step, I'm going to want to collect ground control points and tie points to be able to refine the position and orientation of my scenes from the nominal model. This is important because we need to ensure that the model for both our scenes is adequate for DEM extraction. Now to save us some time, I've already collected the points. So I'm going to close this project, and I'm going to open a project that contains my already collected points. So now that I've opened this new project, the first thing I'm going to want to do is go to my processing step drop-down, go to Model Calculations, and I'm going to click on Compute Model. And the reason why I'm doing this, I'm making sure that my project is completely up to date. So I'm computing the model so I have RMS values and everything's calculated. Now I'm going to go back to my processing step drop-down menu, and I'm going to click on Ground Control Point and Tie Point Collection. The second icon from the right is a Display Project Overview, and I'm going to press on that to open an overview of my images. So right here you can see my two radar SAT scenes. Now I'm going to select both of them, and I'm going to add my ground control points and my tie points. So looking at this right here, you can see that I have a pretty good distribution of my points for both my images, and that my points outline both islands. So next thing I'm going to want to do is have a look at my images in a summary table. I'm going to click on this tool right here, this icon, which is going to open the raw image summary table. Now the raw image summary table and the project overview panel work together. So whatever image I select in the table, you can see that it's being selected in the project overview. Now this is a really great feature, especially when you're working with hundreds of images and you need to identify certain images in your project. So the raw image summary table right here provides a summary on a per image basis within the project. So I can look at the GCPs that I've collected right here. I can see that I have 50 for one image and 55 for the second. And right here I can tell that I have 56 tie points collected for both images. Now I can look at these two columns right here, ground control point RMS and tie point RMS. Now, the RMS of my GCPs and my tie points are a little high, but this isn't surprising. Higher ground control point and tie point RMS in radar projects is actually not, it's quite common, especially when your reference imagery is a 15-meter panchromatic scene. But despite this, I'm confident that I'll be able to extract a good DEM from my points. So I'm going to close this panel now, and I'm going to go back to the processing step drop-down menu. And I'm going to go to DEM from stereo. So I'm going to click on this first icon right here, create epipolar image, to bring up the epipolar panel. So for those of you who are not sure what epipolars are simply images that are reprojected so that they share a common orientation to match features along an axis. The reason why we generate epipolars is because this reduces the amount of processing time required, and it reduces the likelihood of bad matches between our images. So the first thing I'm going to want to do in the epipolar panel, I'm going to want to select a pair. So I'm going to select one image for the left, and I'm going to select another image for the right that corresponds. Then I'm going to click on Add Epipolar Pairs to Table. Now at the bottom right here, you have the downsample factor, and this is the last thing I need to specify. However, for this project, I'm going to be using a downsample factor of 1, which is equivalent to the spatial resolution of my imagery. But if I wanted to use a downsample factor of 2, what that would do would create epipolar images that have twice the spatial resolution of my inputted imagery. Now the epipolar generation process can take some time. So I've already extracted the epipolars and created them, and on my laptop this job took approximately 3 minutes. So the last process in OrthoEngine is the DEM Extraction. And by clicking on the second icon, we bring up the DEM Extraction panel. And the first thing I'm going to want to do in this panel is select my epipolar pair to use to create a DEM. Now before creating my DEM, there's a series of parameters that I'm going to have to specify, and I'm going to go through each one of them right now. So at the top, we have the elevation range option, and we have the option to have it determined automatically or explicitly. OrthoEngine, using the information we've provided, the ephemeris data, all the points, could determine automatically a range for your DEM. But for this case study, I'm going to explicitly set it. I'm going to provide a minimum value of 0, which is the mean sea level. And I'm going to provide a maximum value of 600 meters above mean sea level. Now, this doesn't mean that the highest point in my DEM is going to be 600 meters. All it means is that this is a plausible range of values that I'm giving it. Next, we have the failure value and the background value. Now, I'm going to use the values that are provided here, but just know that any value, any pixel that was not assigned an elevation value is assigned a value of -100 for failure. And any pixel where there is no data to compute an elevation value, that pixel is going to be assigned a value of -150. The next parameter is the DEM detail. Now the DEM detail parameter specifies how much detail we want represented in the terrain. For this project, I'm going to use a high level of detail. The next parameter is the terrain type. Now the terrain type parameter has three options. It has flat, hilly, and mountainous. And each parameter type right here has an internal set of parameters that's best suited for those environments. So for this case study, I'm going to use mountainous as a terrain type. The last parameter I'm going to want to specify is a smoothing filter. And I'm going to set this to medium. Quite often you'll notice that radar DEMs will be a little bumpy and have some pits. So I'm going to use a medium filter to try and resolve those pits and bumps. Now what I'm going to want to do is check this right here, create geocoded DEM. And what this is going to do, it's simply going to geocode the pixels in my DEM. Here I'm going to specify an output file name for my DEM. And the last thing I want to do is specify the output spatial resolution of my DEM. Now for radar DEMs, it's suggested that you apply a spatial resolution that's anywhere between 4 to 6 times the spatial resolution of the image that you inputted into OrthoEngine. So for this application, I'm going to do 4 times the initial spatial resolution. So I'm going to set it to 9.86 and 8.29. And that's all you need to do to prepare the DEM extraction job. But once again, this process can take quite some time to run. On my laptop, it took approximately 22 minutes, so we're going to continue with the DEM that I previously extracted. So I'm going to close this panel now. I'm going to close OrthoEngine. And I'm now going to bring up the DEM that was extracted using my OrthoEngine project file. So right here, this is the DEM that I've extracted. Now at first sight, the DEM doesn't look very good. At least that was my first impression. However, there's a lot we can do with the DEM editing tool to improve this extracted DEM. If you're not familiar with our DEM editing tool, it's an easy and intuitive tool that allows users to apply a variety of operations to improve the quality. Operations such as removing artifacts such as bumps and pits, filtering your DEM to produce a DTM, interpolating failed values or anywhere where there's no data pixels, and there are many other operations available in this tool. So the first thing I'm going to want to do right here, I'm going to want to remove all the effect of the water. So I'm going to go to my DEM editing tool. I'm going to click on this icon right here, open polygon layer, and I'm going to go select a polygon layer that I've already created. So right here, we have my polygon layers. You'll see that I delineated the outline of my islands using a Landsat 8 image. And then I have another polygon that delineates the entire spatial extent of my study site. So what I'm going to do right here, I'm going to click on this polygon, the polygon that delineates the entire spatial extent. I'm going to go to my DEM editing tool, go to the operation drop-down list, and I'm going to select constant elevation. And I'm going to assign a value of 0. Next, I'm going to click on Apply. And once I click on Apply, you'll see that all the pixels within this polygon were assigned a value of 0. So I'm basically burning in the ocean right here. But you'll notice that my islands, the pixel values were untouched because the polygons preserved their values. Now the next thing I'm going to want to do, if we zoom into the island of Terracia right here, you'll see that I have some pits in my DEM. And if we look at the image, you'll see that those pits do not exist. They're not natural features. So I'm going to want to remove those pits from my DEM. So selecting the polygon, I'm then going to go to the operation drop-down list, and I'm going to select on Remove Pits. And I'm going to specify the parameters for that job. So I'm going to set a size of 15, which means I'm going to be using a window of 15 by 15 to identify those pits. And I'm also going to use a gradient as a criteria for pits that need to be filled. So now that I have that set, I'm simply going to click on Apply with Overwrite, and you'll see as I press Apply, those pits are going to start to fill up. And I'm going to run this a number of times until my pits are filled. And I'm going to apply the same operation on my other islands. So as I'm pressing Apply with Overwrite, you can see that the pits are being filled on my island. Okay. Now the next thing I'm going to want to do, I'm going to want to correct an issue that results that is in our DM because of foreshortening. So if we look at our image right here, we can see that the radar image doesn't fully extend to where the Landsat 8 image is, to the slope of the Landsat image, where it intersects the water. And the reason for that, well, is the foreshortening. And that has an effect on our DM. So if we go look at our DM right here, you can see that where the land intersects the water, we go from an elevation of 0 to an elevation of 147. So if in a run of 2 meters, we have a rise of 147 meters. So this is not actually representative of the actual slope, and we need to correct this. So what I'm going to do, I'm going to go back to Open Polygon Layer, and I'm going to open another polygon layer that delineates the slope along this coastline. Now the bottom of the polygon right here represents where the water and the land intersects, and the top of the polygon right here, this is the top of the cliff, where the cliff begins. So I'm going to click on this polygon, I'm going to go to my operation drop-down list, and I'm going to select the operation fill from vertices. And what this operation is going to do, it's going to take all the elevation values underneath the vertices, and it's going to interpolate a nice smooth cliff along the edge. So I'm going to click Apply, and let's see how our slope is going to look. So here you can see our slope looks much better. So if we go down right here, and if you look at the elevation value right here as I go up, you can see that we have a much more gradual slope now. That's more representative of the coastline. Now to finish up editing my DM, there are two things I'm going to want to do. I'm going to want to interpolate any possible failed pixel value, and I'm going to want to smooth out my DM. So I'm going to go to the Edit via Bitmap tab. I'm going to go to Filtering Interpolation, and I'm going to select Interpolate. And I'm going to apply this to my entire DM. And this is going to interpolate an elevation value anywhere there's a pixel value that has -100 for failure. Once that's done, I'm going to apply a smoothing filter. So with radar extracted DMs, you can see that we get a lot of bumps. And I'm going to try and remove a lot of those bumps and just smooth out the overall DM. So I'm going to apply that. And now you can see that my DM is much smoother. So let's go have a look at my other DMs and compare them to this DM right here. So if we look at where I started, the before and after of my DM, you can see that there's a significant improvement in our DM. We had all the effects of the water, those are gone, and then our slope is much nicer now. But let's have a look at this DM and compare it to our other DM products. So what I've done, I've delineated 3 transects, and at each transect we have the topographical profiles of a 25-meter Aster DM from USGS, a 30-meter SRTM DM from USGS, a 90-meter SRTM DM also from USGS, and we have the profiles of my unedited extracted DM and profiles of the edited DM. Now note that the unedited DM, the only edit that I made was I removed the effects of the water. So looking at our first transect right here, if we look at the first peak, which is the island of Terracia, there isn't anything noticeably different. All 5 DMs have a similar profile. However, if we look at the second peak right here, which is the island of Santorini, this yellow line right here is my unedited DM. And then this dashed blue line is my edited DM. And this slope right here is where we had issues due to foreshortening. So by smoothing out my slope, we went from this steep slope right here to a slope that resembles the slope in my other DEM products. For the second transect, the island of Terracia right here has some variation, but that's mostly the 90-meter SRTM. And if we move to the middle, hold on a second, the middle island right here, you can see that our extracted DEMs follow closely with the SRTMs, but if you look at the blue line right here, this is the Aster DM, and it seems that it underestimates a lot of the elevation values on this island. For the island of Santorini, it seems our extracted DEMs underestimates the 2 highest peaks right here. But along the slopes, you'll notice that it's quite similar to both Aster and the 30-meter SRTM. And then you have the 90-meter SRTM, the gray line right here, and you see there's a lot more variation. The third transect is only the island of Santorini. And here we can see there's a little more variation in some areas between all the DMs. And I actually find this to be quite interesting. So if we zoom into the middle right here, you'll notice that none of the DEMs really align. They have very different elevation values, and there's a lot of variation right here. And I found this to be very interesting, that none of the DM products resemble each other. But as soon as we get past this extent right here, and we move towards the end, you can see that all our DM products nicely align with each other once again. So the last thing I'm going to show you all are a series of orthos that I generated using each of the DM products. So I'm going to close this. And I'm going to go back to focus. So right here we have an ortho that was produced using the unedited DEM. And if we flicker between this ortho and a Landsat 8 image, you can see that the slope right here doesn't quite extend to where it should. Now if we look at my ortho that was generated using the edited DM, you'll see that my slope now extends to where it should. So flickering between the Landsat 8 image, you can see that my slope is nicely aligned. So now I'm just going to show you the orthos produced with the other DM products. And interesting enough, you'll notice that there's quite a bit of variation between all my orthos. So if we look at the ortho produced with Aster DM, we can see that there's variation along the coastline right here, and basically throughout the DM, the ortho. And next, if you look at the 30-meter SRTM, you'll see that once again, we have a lot of variations along the coastline right here. And then finally, we have the 90-meter SRTM. So I'm going to go through those once again. So I can't really, comparing all the orthos, I can't really determine if one ortho is better than the other. They all have their differences. So that's basically it. So now that concludes the webinar. Before moving on to questions, I'd like to take the moment to acknowledge MDA for providing PCI with the RadarSat-2 imagery and for the best practices guidelines for scene selection. I would also like to personally thank Dr. Gabriel Gassin, who prepared the Santorini case study for this webinar. So back to you, Kevin.
Great, thanks Jean, and not quite the end of the webinar, just the end of the demonstration there, so please stay with us for a few more minutes as we go through a few more things. We've had some questions come in, and I wanted to bring up a few resources for everyone to consider. So throughout the webinar we've had a series of questions, and a lot of them are actually pertaining to what it is that we offer. So if you do head to our website, you can pull down Software Geomatica and head to the Radar Suite page. This is where you can access the download version of Geomatica if you want to work with it. You can find out exactly what it is that we offer in terms of Geomatica Radar Suite. It is a package of modules that is well suited for not only doing DEM extraction, but other types of analysis from some of the sensors that are listed down here. So you can find out about that. The other thing that's kind of exciting is we have a special offer for archive imagery in partnership with McDonald Detweiler. So if you click on that link, it'll redirect you to a dedicated page that provides just a multitude of resources. If you're new to SAR, we have a bit of a SAR 101 primer section. We have a tab here on learning SAR. So we do have online training available, and there's actually a radar course coming up on December 8th and 9, which is offered through a very similar interface to what we're using here today. It's called Go-To Training. And we also have textbooks. So if you want to actually work through some examples and follow along, you can download the textbooks that we use to provide those online courses. And of course, we have a number of webinars, this being one of them. You can go back and look through the archives and see what other webinars we have available. And under here, we have sample imagery. So one of the data sets that you can freely use is of Vancouver. They do have, MDA does offer freely available stereo radar data over Vancouver, which is actually the subject of a YouTube video which we have available on our channel. And the last thing I'll point out here is our YouTube channel, which has quite a few videos. And if you look under playlists, or you could just use the search feature here, we do have curated playlists on specific topics. So if you're interested in, for example, DEM editing, which is what Jean was showing, we have a specific set of videos that are grouped into a playlist. We also have, for example, if I search SAR DEM on our channel, we have a demonstration that we put together last year at about this time on using the freely available RadarSat data over Vancouver to generate DEMs. So there's a lot of resources available, and I encourage you to find out more about that.